All right, so that's error. Now, all right, couple other things here. Area versus volume. I have a discussion in my book about McDonald's French fries, and I think small cut French fries tend to absorb more salt and grease. And so if you like salt and grease flavor like I do, then small cut fries like at McDonald's or Steak and Shake are pretty tasty, especially when they're hot. If you like the potato flavor, then you want less salt and grease, then you're going to favor larger cut fries like steak fries or fries at Wendy's. I think are bigger than McDonald's. And so and that's because you know, the potato taste is related to volume, but the salt and grease taste is related to surface area. So a larger cut of French fry is going to produce a larger volume, and the volume is going to increase at a third power rate in relation to the surface area, which only increases at a second power rate, and so you get more potato flavor in that case because of the increased volume. Airplanes can only pretty much get so big because the power it takes to drive the airplane in the engine, and when you compare that to the surface area of the wings, it's like skin area and volume again, or weight. That a much larger airplane, the weight grows according to the cube of its length, third power. So weight grows according to third power, but the ability to lift is based upon surface area of the wings, and that's the second power. So it would not be possible to build you know, an unlimited size airplane. The largest airplane ever built was flown once around World War II. It's called the Spruce Goose, and it was built by Howard Hughes out in California. It's made out of wood, and he flew it across a bay up there, and that was it. And it was determined to be just impractical. I think the wingspan was about 300 feet, and it was just an enormous plane. It's humongous, but you just can't you know, build enough power to lift a plane even bigger than that. So you know, those things are impractical. So a lot of these things, I mean, think about length, area, and volume impact the animal world, you know, the physical world. You know, if you drive in the mountains and get stuck behind a truck going uphill, you can pass it very quickly. You know, the power requirement for the truck, even though it has a bigger engine than your car, to some extent its power is limited by its air intake, and the air intake comes across areas, and so there's some issues there with area and volume. And that's why although a huge truck, you know, large trucks, semi-trucks have big engines, big power, they have no acceleration, and so you get behind them going up a hill, they're going to go very slow, and your cars can zip around them. It's kind of like you know, an elephant lumbering up a hill versus a squirrel just zipping up a tree. And so all those things are, again, variation relationships. I'll end with one more. We have a biologist on our South Campus who wrote a master's thesis about the emperor penguin, and as part of his thesis he did some mathematical biology, and the reproductive habit of these penguins is to travel inland, lay the eggs, and inland they're away from their predator, the seals out there that like to eat penguins. So they go inland, lay the eggs, and one of the birds sits on the eggs while the other one travels and gets some food, comes back, and they relieve each other. So I think there's more to it than that, but our biology faculty member was able to argue that these penguins have to be about 3 feet tall. If they were too tall or too short, then the mathematical biology of it would prevent them from having that particular reproductive habit of laying eggs inland. And it would change the bird's habits, and who knows what would happen. So, you know, those are considerations that biologists must use. All right, well, anyway, I hope you found this discussion pretty interesting, because I find it very interesting. This begins to inform us on how nature works, to some degree, at least from a mathematical standpoint.